double slit interference. What's going on? We have a wall blocking a light source, making parallel waves of light. We have two tiny slits, like 1/10 of a millimeter apart, like really close together. And then like a meter away or so, we have a wall. And what happens is, zooming in on it, the light hits these two slits and starts to spread out into like concentric circles. And then these circles are overlapping, and so the two waves are interfering with each other. So in some places they're adding up, and in some places they're canceling. So we want to figure out what's it going to look like when it reaches the screen. We're going to get a pattern of stripes because of the spacings of these places where they're intersecting. So what's going on? First, the center line. If you're directly in the center, that's going to be bright. The two beams are coming from the different slits, and they're in phase the whole way. There's nothing to make a difference. So they will interfere constructively, and you will have a bright spot in the center. But what happens if you go off a little bit? You have these two beams. Now these beams are almost exactly parallel, as you can see. So when I zoom in, I'm going to draw the beams like this, as if they are parallel, but we know they're not. If this is 30 degrees, this is like 29.9999 degrees or something. You know that they're going to meet eventually. But roughly speaking, we can just call them both the same angle. So what's happening is we care what happens in this first little distance. If I drop a perpendicular here, and the separation between the slits is d, then if this angle is theta, and this angle is theta, and this is 90, then this is not theta, this is 90, so this is theta. So we have a triangle here, and this is the crucial thing. Right here, that distance, d sine theta, that is the extra distance that one beam traveled that the other one didn't. That's the only difference between the two beams. It's the only way they could get out of phase. So we care very much how long that path is and how it compares to a wavelength. Because if you have a wave and it does one extra wavelength, you can't tell the difference. The wave looks exactly the same if you delay it one wave or two waves or three waves. But you can definitely tell the difference if you delay it half a wave. Every place up becomes down, every place down becomes up, and it would collide with the original beam and destructively interfere. And so you get darkness. That's why you get dark spots in places. So this d sine theta, we care very much. Is that equal to an integer m times the wavelength? Or is it m½ times the wavelength? And of course it can be all kinds of things in between. We're not as interested in those cases because it's partly constructive, partly destructive. We're mostly interested in the maximum brightness spots, where it's completely constructive, and the minimum brightness spots, the darkness spots, where it's completely destructive. And we mostly don't worry about the times in between. So we're interested in the cases where we have an integer number of wavelengths or an integer plus a half number of wavelengths. And this will be constructive and this will be destructive. So this is how you find the bright zones, and this is how you find the dark zones. Now back to this side. Looking at it in full scale, the screen is going to be at a distance L from the wall with the double slits. The location of the maximum or minimum we get is going to be measured as a distance y from the center line, the line right between the two slits. So how are these related? Well, this angle theta is effectively this angle here. So we have a triangle, and the tangent of theta is equal to y over L. So if you want to know what y is going to be L times tangent of theta. All right, but but we might be finding out the angle from knowing the wavelength and which maximum or minimum we want, and knowing the spacing of the slits. So if we know this, and we know this, we're trying to find out theta. That would give us theta, which we could then put in here and find out what delta y is. Now there's one shortcut trick that they might be using. If the angle is small, and by small I mean like under 6 degrees, with 99% accuracy, you can basically pretend sine theta and tangent theta are the same thing. Try it on a calculator. If you try the sine of 6 degrees and the tangent of 6 degrees, they're very, very close. So they will sometimes approximate things. Here, sine of theta would be, say, m lambda over d. And if they fake it and put that in there, you'd get lmd, lambda over d. And the m being an integer, that actually means these are evenly spaced. Once the angles get big, they won't be evenly spaced anymore. But if you're dealing with small angles, and we often are, then near the center, the lines are evenly spaced, and that can save you a lot of time on calculating. If you know the third maximum is at 6 centimeters, then basically you know all the maxima are every 2 centimeters, at least near the middle. An example. 500 nanometer light shines through 2 slits 0.08 millimeters apart onto a screen 1.2 meters beyond them. How far from the center is the third maximum? All right, identifying what we have. The wavelength is 500 nanometers. D, the separation of the 2 slits, is 0.08 millimeters. We might want to think of that as 8 times 10 to the negative 5 meters. And this could be 5 times 10 to the negative 7 meters. The screen is 1.2 meters beyond, so L is 1.2 meters. How far from the center is the third maximum? Our basic formula is that the path difference, d sine theta, which you might be calling delta x or delta s, that is going to equal third maximum. For a maximum, we want an integer, not a half integer. And so for the third maximum, well, assume they mean the third order maximum. The center maximum is 0. So 1, 2, 3 maxima above that is the third order maximum. So we're going to say m is 3, and the wavelength here, lambda, is 500 nanometers. So if we put this in, we can find theta. Sine of theta is 3 times 5 times 10 to the negative 7 meters divided by d, which is 8 times 10 to the negative 5 meters. And we get 0.01875 is the sine of the angle. If you're in degrees mode, the arc sine of that comes out to theta is 1.074 degrees. And then the tangent of that angle is 0.01873. So you can see it's pretty much the same. That's why the small angle approximation works so well. So that means that the height is going to be, L is 1.2 meters, and tangent theta is 0.01875. So y is 0.0225 meters. So 2.25 centimeters.